2,000 years before Newton wrote a single equation, a man in a small Indian village was already describing how things fall, how numbers behave near infinity, and how the universe counts itself from zero. He did not have a telescope. He did not have a calculator. He had a palm leaf, a stick of charcoal, and a mind that refused to accept "we don't know" as a final answer. His name is barely known outside India today, and he is not alone. There are at least 10 more names like his, buried under centuries of silence, waiting for the world to say them out loud. This is the story of ancient India's greatest scientific minds. Baudhayana. Long before Greece had a philosopher named Pythagoras, India already had the answer to his most famous theorem. Baudhayana lived somewhere around 800 BCE, in a time when the Vedic people of India were building fire altars for their sacred rituals. These altars were not random shapes. They had to be built with exact geometric precision, because it was believed that even a small error in the shape of the altar could break the spiritual power of the ritual. So Baudhayana, a priest and a mathematician, sat down and worked out the rules of exact geometry. In his text called the Baudhayana Sulba Sutra, he wrote down a rule that would later be called the Pythagorean theorem, the idea that in a right-angled triangle, the square of the longest side equals the sum of the squares of the other two sides. He did not just state it, he gave working examples using number sets like 3, 4, 5, 5, 12, 13, and 8, 15, 17, showing that he understood exactly how these numbers behaved. This was roughly 1,000 years before Pythagoras is said to have lived in Greece. But Baudhayana did not stop there. In the same text, he gave a method to calculate the diagonal of a square, which is mathematically the same as finding the square root of 2. His approximation was accurate to 5 decimal places. Think about that. A priest using a rope and a stick, working purely from logic and careful measurement, arrived at a value that modern calculators confirm today. Baudhayana's work reminds the world of something important. Mathematics in India did not begin as an abstract hobby for scholars. It began as a practical, sacred, deeply human effort to get things exactly right. And in getting it right, he quietly became one of the first geometers in recorded human history. Sushruta. Around the 6th century BCE, in the ancient city of Kashi, on the banks of the river Ganga, a physician sat beside his students and calmly explained how to rebuild a human nose using skin from a person's own cheek. This was not science fiction. This was Sushruta, and this surgery is still performed today, almost unchanged in its basic principle. Sushruta is known as the father of surgery, and that title is not an exaggeration. His text, the Sushruta Samhita, describes more than 300 surgical procedures and around 120 different surgical instruments. Long before anesthesia, as the world understands it today, Sushruta had already worked out ways to manage pain, prevent infection, and care for a patient after an operation using ingredients like wine and dressings made from ghee, honey, and turmeric. Substances modern science now confirms have real antiseptic properties. His most celebrated achievement is the rhinoplasty, or nose reconstruction surgery. In ancient India, cutting off someone's nose was sometimes used as a punishment, so Sushruta developed a method to rebuild it using a flap of skin taken from the patient's own forehead or cheek. This technique survived for centuries in India, passed down through generations of traditional healers. In the late 1700s, British surgeons in India witnessed this exact procedure being performed successfully and were stunned. They wrote about it, took it back to England, and by the 1800s, this ancient Indian technique had become the foundation of modern plastic surgery. Sushruta also described a method for cataract surgery using a curved needle to carefully push the clouded lens out of the way so a patient could see again. He performed cesarean deliveries, treated bladder stones, and even described early signs of diabetes by testing the sweetness of a patient's urine. Recognizing a disease that modern medicine would only fully explain thousands of years later. Every time a surgeon today reconstructs a damaged face or removes a cataract, they are, whether they know it or not, walking a path that Sushruta first cleared with nothing but instruments he designed himself and a deep respect for the human body. Kanad. Before John Dalton proposed the modern atomic theory in the 19th century, an Indian philosopher was already asking the same question while eating his food. His name was Kanad, and historical estimates about exactly when he lived vary quite a bit, ranging anywhere from around the 6th century BCE to a few centuries into the Common Era. What is certain is that he founded a school of Indian philosophy called Vaisheshika, and within it, he built one of the earliest known theories of matter in human history. According to the accounts passed down about him, Kanad was once walking with food in his hand, breaking off small pieces and eating them. At some point, the pieces became so small he could not divide them any further. That simple, everyday moment made him ask a much bigger question. If you keep dividing matter, is there a final, smallest piece that cannot be divided at all? He called the smallest indivisible unit of matter paramanu, which translates roughly to atom. He proposed that these paramanu were eternal, that they could not be created or destroyed, and that they combined with each other to form everything in the physical world. He even described a two-atom combination he called dwinuka, something remarkably close to the modern idea of a molecule. He suggested that different combinations of these tiny particles produce all the different substances we see and touch. Now, it is important to be honest here. Kanad's atomic theory came from logic and philosophical reasoning, not from laboratory experiments the way modern chemistry works. He did not have instruments to prove it, but the fact that a thinker, working purely with observation and reason, arrived at the idea that matter is made of indivisible building blocks, roughly 2,000 years before Western atomic theory took shape, is nothing short of remarkable. It shows that the instinct to look for the smallest truth of the universe has lived in the Indian mind since ancient times. Charaka. While the Western world often credits Hippocrates as the father of medicine, India has its own physician who deserves equal recognition, Charaka. Most historians place Charaka's work somewhere between 100 BCE and 200 CE, though the tradition and knowledge behind his writing is older, based on an earlier text by a scholar named Agnavesha. Charaka revised and expanded this work into what is now called the Charaka Samhita, one of the two foundational texts of Ayurveda, alongside Sushruta's work. What makes Charaka extraordinary is how modern his thinking sounds, even today. He described the human body as an interconnected system, explaining ideas that closely resemble digestion, metabolism, and immunity, concepts that Western medicine would only formally name centuries later. He organized health around three core principles he called doshas: vata, linked to movement; pitta, linked to transformation and metabolism; and kapha, linked to structure and stability. When these three fall out of balance, he argued, disease follows. Charaka also insisted that every patient is different. He spoke about individual constitution, shaping how a person responds to food, medicine, and lifestyle. An idea that modern medicine now calls personalized medicine, something hospitals are only beginning to fully embrace in the last few decades. He recognized the existence of tiny invisible organisms he called krimi that could cause disease, showing an early awareness of the idea of pathogens long before microscopes existed to prove it. Perhaps his most quoted piece of wisdom is this: "It is more important to prevent disease than to cure it." In a world today obsessed with wellness, prevention, and holistic health, Charaka was already saying all of this thousands of years ago. He did not just treat illness, he tried to understand life itself. Pingala. Here is something that will genuinely surprise most people. Long before computers existed, an Indian scholar studying poetry stumbled onto the exact system that powers every computer, phone, and satellite on Earth today. Pingala lived sometime around the 3rd or 2nd century BCE. He was not trying to build a machine, he was trying to solve a problem in Sanskrit poetry. Poetic verses in Sanskrit are built from syllables that are either short, called laghu, or long, called guru. Pingala wanted to systematically calculate every possible combination of short and long syllables for a verse of a given length. To solve this, in his text called the Chanashastra, he created a system that assigned values to these syllables in a pattern that is mathematically identical to modern binary code. the same system of zeros and ones that runs every computer chip in the world today. This happened roughly 2,000 years before Gottfried Leibniz, the European mathematician credited with formalizing binary numbers in the 17th century. But Pingala did not stop there. While working out these combinations, he also created a numerical triangle called the Meru Prastara, or the Mount Meru arrangement. This triangle is structurally identical to what the world today calls Pascal's triangle, named after the French mathematician Blaise Pascal, who lived nearly 2,000 years after Pingala. Even more incredibly, when you add up the diagonal rows of Pingala's triangle, you get the exact sequence of numbers known today as the Fibonacci sequence. The same sequence found in flower petals, pine cones, and spiral galaxies, and credited to the Italian mathematician Fibonacci, who lived over 1,000 years later. Pingala was a poet chasing rhythm and pattern in language. What he found instead was a mathematical structure so fundamental that it now sits at the heart of modern computing, probability, and nature itself. It is one of the most beautiful accidents in the history of human thought. Number 6. Aryabhata. If there is one name that deserves to be a household word across the world, it is Aryabhata. Born in 476 CE, most likely in the region of Kusumapura, present-day Patna in Bihar, Aryabhata wrote his most famous work, the Aryabhata, at just 23 years old. In this single text, he laid the groundwork for centuries of mathematics and astronomy that would follow, not just in India, but eventually across the Islamic world and Europe as well. Aryabhata introduced a place-value number system built on a base of 10, the same decimal system the entire world uses today. While there is ongoing academic debate about whether he used an explicit symbol for zero, scholars agree that the concept of zero as a placeholder was clearly embedded in his system, laying essential groundwork for the formal use of zero that would follow shortly after him. He also calculated the value of pi with startling accuracy. In his own words, translated from Sanskrit, he gave a method that comes out to 3.1416, a number remarkably close to the true value of pi, calculated using nothing but geometric reasoning and careful arithmetic, at a time when most of the world had no comparable method. But perhaps his boldest idea was about the Earth itself. Aryabhata proposed that the Earth rotates on its own axis, and that this rotation, not the movement of the stars, is what creates the illusion of the sky moving above us. He compared it to a person sitting in a moving boat, watching the riverbank appear to move backward, even though it is the boat that is actually moving. This was a genuinely radical idea for his time, proposed roughly 1,000 years before Galileo would face persecution in Europe for defending similar ideas about the Earth's motion. Aryabhata also correctly explained that the moon and planets do not produce their own light, but instead reflect sunlight, and he gave accurate explanations for solar and lunar eclipses based on the geometry of shadows, not superstition. In 1975, independent India chose to name its first satellite Aryabhata, launched into space as a tribute to a mind that looked at the sky 1,500 years earlier and got so much of it right. Number 7. Varahamihira. In the intellectual capital of Ujjain, often called the Greenwich of ancient India because of its role as a reference point for astronomical calculations, lived a scholar whose curiosity refused to stay in one lane. Varahamihira was born around 505 CE and lived until roughly 587 CE. He was known as one of the Navaratnas, or 9 gems in the royal court of his time, a group of the most brilliant scholars gathered in one place. His most celebrated work, the Panchasiddhantika, is a remarkable piece of scientific honesty. In it, he collected 5 different existing astronomical systems of his era, compared them side by side, corrected their errors, and proposed improved calculations of his own, particularly around the precession of the equinoxes. This was not blind faith in tradition. This was rigorous comparative science. His other major work, the Brihat Samhita, is almost impossible to categorize because of how much ground it covers. It includes sections on astronomy, architecture, agriculture, gemology, and, most fascinating of all, one of the earliest known systematic attempts at weather forecasting. Varahamihira studied planetary positions, wind patterns, and natural signs like the behavior of animals and plants, and used them to predict seasonal changes and weather patterns. He is also remembered for early techniques used to identify underground water sources, a practical skill that combined careful observation of land, vegetation, and geography. What makes Varahamihira remarkable is not just what he discovered, but how he worked. He treated knowledge as something to be tested, compared, and refined, not simply repeated. In an age when much of the world explained natural events through myth alone, Varahamihira was building frameworks, testing them against observation, and writing down what actually held up. That is, in essence, the scientific method, practiced in India in the 6th century, long before the term itself was invented in Europe. Number 8. Brahmagupta. Aryabhata gave the world the idea of zero as a placeholder, but it was another Indian mathematician, born about a century later, who taught the world how zero actually works. Brahmagupta was born around 598 CE in a region called Pingala, in what is today Bhinmal, Rajasthan. At the age of 30, in the year 628 CE, he completed his masterpiece, the Brahmasfuta Siddhanta, while serving as the director of the Astronomical Observatory at Ujjain, the same city where Varahamihira had worked before him. In this text, Brahmagupta did something no mathematician before him had done with this level of clarity. He gave formal rules for how to add, subtract, and multiply using zero, and he treated zero not just as a placeholder, but as a number in its own right, describing it as the result of subtracting a number from itself. He called positive numbers dana, meaning fortune, and negative numbers rina, meaning debt. And he laid out precise rules for how these numbers behave when multiplied and divided. His sign rules: a positive multiplied by a positive is positive, a negative multiplied by a negative is positive, a positive multiplied by a negative is negative, are exactly the same rules taught in classrooms across the world today. He did make one now famous error, claiming that 0 divided by 0 equals 0, a claim modern mathematics considers undefined. But even this mistake shows the extraordinary depth of thinking he was attempting on a concept nobody had systematically tackled before. Brahmagupta also gave the world one of the earliest clear descriptions of the quadratic formula, the same formula still taught to algebra students everywhere. He developed a formula for calculating the area of a cyclic quadrilateral, a shape whose four corners all touch a single circle, a result still referred to today as Brahmagupta's formula. He worked on indeterminate equations, solved complex problems involving interest rates and finance, and even developed early tools for astronomical prediction, later refined in his second major work, the Kanad, written in 665 CE. Because of Brahmagupta, 0 stopped being just a placeholder in a number system and became a true number, with its own rules and its own logic. One of the most consequential ideas in the entire history of mathematics, and it came from India. Number 9. Nagarjuna. Before there was a formal science called chemistry anywhere in the world, India already had scholars melting, purifying, and transforming metals in working laboratories. It is important to be upfront about something here. Historians do not fully agree on who Nagarjuna the alchemist actually was, or exactly when he lived. There is a famous Buddhist philosopher named Nagarjuna, and separately a tradition of an alchemist and metallurgist who is also called Nagarjuna, and scholars have long debated whether these were the same person or two different people who share a name. Most careful historical estimates place the alchemist Nagarjuna somewhere between the 2nd and 8th centuries CE, with strong evidence connecting him to the rise of Rasashastra, the branch of Ayurveda focused on using purified metals and minerals as medicine. What makes Nagarjuna worth remembering is the sheer practical chemistry involved in his work. Texts associated with him, including the Rasindra Mangala and the Kakshaputa Tantra, describe detailed methods for purifying mercury, working with sulfur, and processing metals like gold, silver, tin, copper, and zinc. This was not casual experimentation. These texts describe specific laboratory equipment, controlled heating processes, and multi-step purification techniques that closely resemble the kind of methodical, repeatable procedures modern chemistry depends on. One especially striking detail is around zinc. India's ancient texts, including references connected to Nagarjuna's tradition, describe distilling zinc from its ore, a genuinely difficult metallurgical process because zinc turns into vapor before it melts as a liquid, unlike most other metals. Getting pure zinc requires precise control of temperature and a proper distillation setup. Long before modern industrial chemistry existed, Indian metallurgists working in this tradition had already solved this problem well enough to produce usable zinc metal. Nagarjuna's tradition also worked extensively with mercury, developing methods to convert it into stable compounds believed to have medicinal properties, a practice that, while rooted in a very different worldview from modern pharmacology, still required real chemical skill to safely process one of the most reactive elements known to humanity. Whatever the exact identity or dates of the man behind the name, the tradition he represents shows that ancient India was not only asking philosophical questions about matter, the way Kanad did, but was also rolling up its sleeves and physically transforming matter in working laboratories centuries before the word chemistry existed anywhere in the world. Number 10. Bhaskara II. Fast forward to 1114 CE in what is now Karnataka, and a mathematician is born who would go on to be called Bhaskaracharya, Bhaskara, the teacher. At the age of 36, in the year 1150 CE, Bhaskara II completed his masterpiece, the Siddhanta Shiromani, meaning crown of treatises. This enormous work of nearly 1,450 verses was divided into four parts. The Lilavati focused on arithmetic, the Bijaganita focused on algebra, the Grahaganita focused on planetary mathematics, and the Goladhyaya focused on spheres and astronomy. The Lilavati, according to popular tradition, was named after his daughter, and it remains one of the most elegant math textbooks ever written, using storytelling and riddles to teach arithmetic, geometry, and basic algebra in a way that made learning genuinely enjoyable. But it is Bhaskara's other work that places him in the same conversation as Isaac Newton. Centuries before Newton and Gottfried Leibniz independently developed calculus in Europe in the late 1600s, Bhaskara had already explored the core idea behind differential calculus. Understanding how a quantity changes at a specific instant, he applied this thinking to planetary motion, working out how the position of a planet changes moment to moment, an idea strikingly close to the modern concept of a derivative. Bhaskara also described a design for what he claimed would be a perpetual motion machine, and he engaged deeply with the concept of infinity, cautiously exploring what happens mathematically when you divide a number by zero. His work traveled through Islamic scholars and eventually influenced mathematical thought in the Middle East. And centuries later, a Persian translation of the Lilavati in 1587 helped keep his legacy alive across cultures, long before Europe would come to fully recognize what an Indian mathematician had already worked out 500 years earlier. Number 11. Madhava of Sangamagrama. If there is one final name that could rewrite how the world teaches the history of mathematics, it is Madhava. Madhava of Sangamagrama lived from around 1340 to 1425 CE in a small village in present-day Kerala. He founded what historians now call the Kerala School of Astronomy and Mathematics, a group of scholars who, over the next 2 centuries, developed mathematical ideas so advanced that some historians consider them a genuine precursor to European calculus. Madhava was the first mathematician in recorded history to develop infinite series expansions for trigonometric functions like sine, cosine, and arctangent. In simple terms, he found a way to represent complicated curve functions as an endless sum of simpler terms, a method that allowed for incredibly precise calculations. Using this technique, he calculated the value of pi to an extraordinary degree of accuracy, using an infinite series method that would not appear in European mathematics until James Gregory and Gottfried Leibniz developed similar series roughly 250 years later. In fact, in parts of the modern mathematical world, this exact series is now respectfully called the Madhava-Leibniz series, acknowledging that an Indian mathematician got there first. Madhava's students and successors at the Kerala school, including scholars like Nilakanta Somayaji and Jeshtadeva, continued and expanded his work for generations, building an entire mathematical tradition around ideas of infinite series and limits, concepts that sit at the very heart of what the world now calls calculus. While Madhava and his school did not unify these ideas into the single, complete framework that Newton and Leibniz would later formalize in Europe, the conceptual seeds were unmistakably present, growing quietly in Kerala 2.5 centuries before calculus became a subject taught in European universities. So many brilliant minds, spanning nearly 2,500 years of unbroken curiosity from the banks of the Ganga to the villages of Kerala. They did not have laboratories with modern instruments. They did not have universities with international funding. What they had was patience, observation, and an unshakable belief that the universe was worth understanding, piece by piece, number by number, syllable by syllable. The West gave these ideas their modern names: calculus, binary code, the atom, the Pythagorean theorem. But long before those names existed, India had already been living inside these ideas for centuries. It is not about taking credit away from anyone. It is about giving credit to everyone who deserves it, including the ones history quietly left out. The next time someone claims a great idea belongs only to one civilization, remember these names. Because long before the world was counting in zeros and ones, a poet in ancient India was already there, syllable by syllable, discovering the pattern of the universe. If this story moved you even a little, share it with someone who still thinks inventions only belong to the West. India has always been thinking. The world just wasn't listening yet.